Hello, welcome to the next lecture on signals and systems. And in this lecture, we will be talking about classification of signals. Till now, we were dealing with only signals. So now we will move on to the concept of system, right? Basically, what is a system? System is a black box, right? It takes in an input x of t and it gives an output y of t. So this y of t, but the thing is that okay, this can be any physical system, but we need to model it mathematically, right? Otherwise we cannot deal with it properly. So we cannot analyze it, we cannot realize it, whatever. So what we do is we try to model it mathematically. So we describe y of t as, how do we do it? Y of t as t of x of t, right? Where t is a sort of transformation done. Some sort of transformation. We don't know what sort of transformation. That transformation, whatever transformation is happening, that is what describes the system. Okay, so basically a system which we designate as t is a mathematically describable operation or transformation that acts on an input signal to produce an output signal, right? That is, the system acts on the input and gives an output, and it should be mathematically describable. We should be able to describe what this t is. Okay, and when it comes to discrete time, it will be x of n and y of n, right? That is y of n, sorry, the notation, y of n is equal to t of x of n, right? Again, t is a transformation. Okay, two things that we basic some sort of an assumption that we make regarding the system is that at t equal to minus infinity, right? At t equal to minus infinity, the system is at a zero energy state or a ground state or a relaxed state. That is, at a long time ago, or at some point of time in the past, the system was completely relaxed, or it was not at all excited, or it is at a ground state. And after that only, that is, initially it was relaxed or zero energy or ground state, then some sort of excitation was given to it, and then it is responding. That is one of the assumptions that we make, right? The other thing is that the behavior of the system is governed by two things. One is the input to the system, and two, the state of the system. That is, whenever we are giving an input to a system, not only does the input have some effect on the output, but that output depends also on the current state of the system. Okay, that is what we are assuming. That is a basic understanding of what a system is, and some basic assumptions also regarding that. Now what we will do is we will move on to the classification of systems. Okay. So depending on certain properties of the system, like we classified signals into certain categories, we can also classify systems. So the first classification is regarding whether a system is linear or non-linear. Okay, whether a system is linear or non-linear. So what we'll do is we'll give the definition for a linear system, and whichever system which doesn't fall or which doesn't satisfy this condition, the criteria, we will call it as a non-linear system. Okay, for linearity, the thing is that it should satisfy two properties. First thing is additivity, and the second thing is homogeneity. Right. What is additivity? Additivity is that if x1 of t gives y1 of t and x2 of t gives y2 of t, that is as the output of the system, then x1 of t plus x2 of t should give y1 of t plus y2 of t as output. That is, if an signal x1 of t individually gives y1 of t as the output and a signal x2 of t individually gives y2 as the output, then the combination x1 of t and x2 of t when given to the input, it should give y1 of t plus y2 of t as the output. Okay, the same thing applies for the discrete version also, right? That is, instead of t it will be n. Then what is homogeneity? That is, homogeneity is if x of t gives y of t, then c into x of t should give c into y of t. Right, that is when if the input is multiplied by a constant, the output should also be multiplied by the same constant. In fact, we can multiply the we can combine these two properties, right? We can combine these two properties and we can write it as a single thing. That is, if x1 of t gives y1 of t and x2 of t gives y2 of t, then we can write a x1 of t plus b x2 of t should give a y1 of t plus b y2 of t, right? This is so these are the conditions for linearity taken separately, and these are the conditions for linearity taken together as one, right? And this property is called as superposition. I hope you remember you did learn something very similar, very much similar to this when you learned network theory. The name was superposition and it was pretty much the same thing. Okay, so if a system is linear, it means that system follows the principle of superposition, or separately taken it follows additivity and homogeneity. Any system which doesn't follow this is non-linear. Okay. For example, right, let's say an example. Consider the system y of t is equal to log of x of t. Okay, here log is the transformation. This is the system actually, right? So what is log of x1 of t plus x2 of t? It is right, it according to our superposition or additivity, it should be what? Log of x1 of t plus log of x2 of t, right? But it is not the case. Therefore, this is non-linear. Similarly, we can take other systems, right? For example, we can take an example of a linear system would be what would be a linear system? For example, y of n is equal to x of n minus 2, right? So then what would x1 of n would give y1 of n, right, which is equal to x1 of n minus 2. Simply a time shifting operation is done. And similarly, x2 of n would give y2 of n, which is x2 of n minus 2. Therefore, x1 of n plus x2 of n would give what? Obviously, it will give x of n minus 1 2 plus x1 of n minus 2 plus x2 of n minus 2, right? So basically this is following the linearity principle, right? Even if you give some sort of constant here, suppose some a and b, right, it will be coming like that only, because this is just a time shift and it will be followed. So this is an example of a linear and so this is linear, right? So this is an example of a linear and a non-linear system. Okay, now the next what do you say, important property is time invariance versus time let's call this time invariant systems. Okay, time invariant system versus time variant systems. Time invariant is also called as shift invariant. Similarly, this will be called as shift dependent. Okay, so what is the idea? That is right, time invariant and time variant. So the thing is that if x of t gives y of t, then x of t minus t0 should give y of t minus t0. That is, if you shift the input by a certain much, the only difference at the output should be that the output is also shifted by that much. No other change should happen. Otherwise, the shape or let's say the shape of the response. What do you mean by the shape of the response? Because here response and input and output are signals, right? So the shape of the response signal should be dependent only on the shape of the input. That is, if you shift the input signal by some amount, the shape of the output signal should not change. For example, let's say our input is like this and our output is like this. Okay, so if you give an input like this, and if the output is like this, right, that is, if you're shifting the input and your output is like this, then this is time variant. But if your input is like this and your output is like this, and if you are shifting the input like this and your output is the same shape but shifted by a little bit, then this is time invariant. That is the basic idea. So a shift in time, a time shift in the input should only manifest as a time shift in the output, right? It should not affect the shape or the expression of the output signal. That is the basic idea behind time variant and time invariant. Okay. So to see if, to check if, how do you check if a system is time variant or invariant? How do you know that? So basically what you take is, you have this, you will have this relation x gives y, right? So what you do is, you take some, you take y1 of t as the shifted version, or right, you take the y1 of t as the output you get when you shift this, as shift the input, and you take, you see how t minus t0 will be. We will see an example. You will understand it more once you see an example for both. Okay. So consider the system, what we did earlier, log x of t. Okay. So what is happening if we shift the input? It is log x of t minus t0. Okay. That is, input is shifted. Okay. Now how should y of t minus t0 look? Y of t minus t0 means all the time components of the expression should be shifted, right? That is log of x of t minus t0, right? That is, output is shifted, let's say, not exactly. So here what you can see is, if you shift input, then you are getting the same as the, if you shift the input, the output you get is the same as the shifted output. So therefore this is time invariant. Okay, it's time invariant. Now consider this example, y of t is equal to e to the power t x of t. So again we are just in shifting the input, that means e t to the power of x of t minus t0. Okay, so this is the output you get if you here you are giving. Okay, so if you are just shifting the input, this is the output you are getting. Okay, now what is the expression for the output if your output is shifted? Then it will be e t minus t0, that is, all the time expression should be shifted, right? But these are not the same, right? That is, if you are shifting the input by a certain amount, you are getting one expression, and if you are shifting the whole output by a certain amount, the same amount, you are getting a different expression. These are not the same, right? This is not equal to this, but here it is equal to this. Therefore this is time invariant and this is time variant. So this time invariance and linearity are sort of important, and combined together they are called as linear time invariant systems, or in short form LTI systems. The systems that we'll be dealing with in this course, and even in your mostly in your control system courses, will be LTI systems, because only if the system is linear and time invariant we can predict the output properly. If it is not, then if the input is shifted by something, if the output we are not able to predict, or if it is changing randomly, or if it doesn't follow linearity, that is, if we are not able to give we are not able to predict the output of a composite signal, then we won't be able to apply Fourier analysis. So therefore that systems we cannot model properly, and most of the signal systems that we model will be linear time invariant or LTI systems. So this is a sort of, it is a class of systems. LTI systems are a class of systems. Okay. Now moving to our third property, which is causal and non-causal systems. Okay. So what does causality means? A causal or a, what do you call, or non-anticipating. Causal or a non-anticipating system is a system which does not depend on the future values. What does not depend on the future values? Current output. Current output does not depend on the future values of the input. For example, consider the system y of n is equal to 2 to the power of n x of n plus 1. Okay, so here what is happening here? The output x of 1 is equal to 2 to the power of 1 x of 1 plus 1, or 2 x of 2. That is, the output, the first sample of the output is depending on the second sample of the input. That is, the current output is dependent on the future input. That is something we don't know yet, right? That is, it is anticipating some sort of input. This is a non-causal system. Right? That is, if the output expression for output is dependent on the future signals, future values of a signal, then it is called a non-causal signal. So causal signals, systems. Causal systems are systems which doesn't do this, which doesn't depend on the future values of input. Okay, current values of output does not depend on the future values of input. That are causal systems. Example for causal system will be, from the same thing you can write y of n is equal to something like this. So here you might feel that, okay, here 2 to the power of n plus 1 is coming, but that doesn't matter, because whenever we are considering causality, we are thinking about how does the output depend on the input. This doesn't matter. Okay, what matters is what term is coming inside the input, or which term, which sample, or what time of the input is the output dependent on. Here, since it is not dependent, for example, y of 1 will be 2 to the power of 2 x of 1, right? That is, it is depending on the current value only. This is a causal system, right? It shouldn't depend on the future value, means it can depend on current and past values of input. Okay, for a causal system. That is a causal and non-causal system. So this non-causal systems are usually not yes, sort of practicable in the sense it is difficult. We have systems which can predict the future values, but that is not exactly, you cannot say that they are non-causal systems. It is difficult to implement non-causal systems. Okay. The next one is static or memoryless versus dynamic or with memory systems. Okay, right. So for a static or memoryless system, what does it mean? What does it mean? It means that output depends only on current input. Okay, so this sort of seems like causal systems. So statics or memoryless systems are causal systems. What about dynamic or memory systems? Output depends, right, output depends on past and or future values of input also, right. That is, you may have terms here, you will have terms like x of t or x of n only in the input, right. But here you may have terms like x of t plus a, x of t minus a, x of n plus b, or x of n minus b. So these are non-causal systems, that is, it depends on future values. These are memory, so dynamic systems only, but they are also causal because they are depending on past values, right. That is the difference. Static means it depends only on the current values of the input, but dynamic means it can depend on the past or future, or it may be a combination of multiple things. Okay, for example, y of n is equal to n plus 1 x of n, and y of n is equal to x of n plus 3. Okay, so this is a static system because it is depending only on x of n. This is a dynamic system because it is depending on future values. This is not a causal system. What if it was x of n minus 3 into, say, n into x of n minus 3, then also it would have been a dynamic system, but it would have been also a causal system. Okay, so that is the static and dynamic, or memory, memoryless and with memory. Okay, so the next classification is regarding the stability, stable and unstable systems. So when is a system said to be stable? Right, when is a system said to be stable? That is, if x of t is less than or equal to mx less than infinity, right. That is, if the input, let's say the absolute value of the input, is a finite value, then the absolute value of the output should also be some sort of finite value. If the input you give is a finite value, then for that corresponding input the output should be a finite value. This is the condition for stability. It is also called as bounded input, bounded output, BIBO. Okay, bounded input, bounded output stability criterion. That is, if the input is bounded or finite value, output also should be bounded, that is a finite value. Okay, that is the condition for stability. A system which does not follow this input this condition is a unbounded system, right, or unstable system. Okay, so the last classification is invertible versus non-invertible systems, right? So what does it mean? It means for a system T, okay, we have an input x of t, we have an output y of t, right? The system is invertible if we can design a system T inverse such that if you give y of t as input, you should get x of t as output. That is, a system is invertible if you can design a system such that T inverse such that if you give the output of the original system as the input, it should give the input of the original system as the output, right? This happens only if what distinct values of x of t produces distinct values of y of t, right? If a multiple number of input values produce the same value of y of t or output, you cannot you cannot invert a system, because you wouldn't know which value of y of t to map to which value of x of t. So if distinct values of input x of t produces distinct values of y of t, then that system is invertible, and this system is called as the inverse of the original system. Okay, this is an inverse system. So you can write x of t y of t inverse and x of t, and the other thing is that t into t inverse should be an identity. Identity what? Identity matrix. Why are we writing like a matrix? Because usually systems can also be represented as matrices when it comes to the discrete or digitization of systems. We can write them as matrices, and the actual matrix of the system and the inverse matrix, the product should be identity matrix. So this was regarding the classification of systems. What were the first one was linear and non-linear. That is whether the system followed superposition principle. Then we had time invariance and time variance. That is whether a shift in input only shifted the output by the same much, or whether it affected the shape of the signal or not. If it affected the shape, it was time variant, and if it didn't affect or just shifted the output, it is a time invariant. And time linear systems which follow linearity and time invariance, they are called linear time invariant systems. They are a class of systems which we can actually model, right? LTI systems. We also saw how we can determine whether systems are linear, and how we can determine whether systems are time invariant. Okay. Then we went for the concept of causal and non-causal, whether the output of the system depends on the future values of the system of the input or not. If it depends on the future values, they are called non-causal, and if it only depends on the current and past values, they are called as causal systems. Okay. Then we went through the concept of static and dynamic, or memoryless or with memory, right? That is whether the output depends only on the current values of the input or future and past values of the input, right? Then we went for the stability condition, the bounded input bounded output stability. That is for bounded for inputs which are having finite values, the output should also be having finite values. And finally we went for invertible and non-invertible system. That is we should be able to design something like this: a system when given the output of the original system should give the input of the original system. And we mentioned that for a system to be invertible, it should be such that distinct values of x of t produces distinct values of y of t. This was the condition for a system to be invertible. So with this I am stopping this lecture, and in the next lecture we will see some examples regarding the classification of systems. Thank you.